Hello and welcome to Group 10's presentation for the CS5593 Data Mining course, Summer 2022, University of Oklahoma. My name is Shane Scourin and I'm joined in this presentation by my classmate Chris Womack. Our project is titled Prediction of UAV and Non-UAV Devices Through Wireless Packet Capture. The agenda for our presentation is as follows. We'll start with an introduction of what UAV detection is and the project objectives. We'll go into related work in this field. Then we'll discuss our proposed work and results. This includes data files and preprocessing, classification algorithm and results, and clustering algorithm and results. We'll talk about conclusions from our work, future work proposed, and we'll go into a software demonstration. Unmanned aerial vehicles, or UAVs, are inexpensive and commercially available. On the right, we have an example of a popular commercial UAV known as the Parrot Bebop 1. Although UAVs like this are practical for things like photography or entertainment, they can also be a threat to physical security and privacy because you're not always able to see or hear when they're coming. Commercial UAVs like this use the Wi-Fi standard, or the 802.11, to communicate between the controller and the UAV. So by using a wireless sniffing program, such as Wireshark, we can collect this packet data and analyze it to determine its source. For our project, we had three objectives. First, we want to take pre-collected wireless packet data and create an application that can read this data and do classification and clustering with it. For our classification, we want to do UAV detection by implementing, testing, and visualizing the algorithm that can detect traffic greater than 90% accuracy and less than 20% false alarm rate. For clustering, we want to generate traffic patterns, implement, test, and visualize a clustering algorithm to demonstrate patterns in traffic that can be corroborated empirically, greater than 50% of the time. In the last few years, there's been quite a bit of research into UAV detection. In 2021, NI determined that active radar, passive radar, and computer vision have been effective in detecting UAVs, but they're generally expensive and limited in range. In 2018, Zhao collected UAV wireless data and created a machine learning algorithm that was cost-aware that could do online UAV detection. In 2019, Cian Selapur detected and localized UAVs through Wi-Fi packet size and inter-arrival time. And in 2020, Ali Porfinade used random forest and support vector machines to not only detect the UAV but also their operating mode based on their packet data. The data set that we're using for this project is based on collection done by Zhao in 2018. There are 6 files that we're using, and that consist of traffic data from 3 different UAVs and various non-UAV devices that have been separated by file. Files 1, 2, and 3 are bidirectional, so that means they measure the packet size and the packet inter-arrival time to the receiver, from the receiver, and the total, which comes out to 55 attributes and 1 label. Files 4, 5, and 6 are unidirectional, so they measure only in one direction, which causes it to be 18 attributes with 1 label. In total, we have over 60,000 labeled instances to do data mining on. The data did not have much missing data or any extraneous data, but our program is able to replace that with the column mean and to discard any rows that have extraneous data. We also did some dimensional reduction for classification. We use the cosine similarity matrix on the right that's generated when the program reads a file to see which features can be eliminated in order to speed up the classification algorithm.
This is Chris Womack. I'm talking about Bayes algorithms that we were implementing on this project. This is the metrics that we used for the data, as it was all continuous data, wasn't discrete. So we had to maintain the variance and the mean of each attribute. You see in this table here, we have A1 through AN, which represents the number of columns in the file. And I would go through, determine which ones had yeses, UV was present, which ones were no's, and I would calculate the variance and the mean for each of those cases. And this information was recorded in this table, and we would use this later during our tool execution to provide prediction and classification. You can see also that I have some metrics that I maintained. I have the components of the confusion matrix and the probabilities that a UV were present or not present in this model that we're verifying here. I also show the model accuracy, and like I said, there's other ancillary information there as well. Moving on to the next slide, you can see here's an actual representation of what that table looks like. So of course, this is abbreviated because it's a number of columns in here will not fit on the screen. But you can see in the upper left, this is attribute 1, and then the second column is attribute 2. So then you can see the first 4 rows are the significant for calculating the probability. Realizing that we're using the normal probability density function. You can see of course, the last column, the second from the last, you can see it's all zeros. That's one of the columns that determined that we were going to reduce the dimensions on. The very last column has the model ID, the binder ID. Then it has the accuracy. You see it's a 99%, which is fairly good for this particular set of files. And then you have the probability of UV present, and then the probability of UV not present being 55 and 44% in this particular data file. As you can see, I got here below the, actually got the confusion matrix for this run. You can see we had a 1551 negatives, true negatives, and I had 1974 true positives, and I had 1 false negative from the model prediction, which was not too bad. It was actually fairly good. On this slide, I show the user interface for Bayes classification. The operator had a choice between 3 different modes, and it's done by using a radio button, a default, auto select, and a user select option. When choosing user select, the 6 columns have to be specified. These will be the ones that will be used for classification. On this slide, I show the 3 modes that were implemented in the tool, and I'll describe those in a little more detail. The default mode selection would allow the software to perform classification using all valid attributes. Any attributes that were eliminated due to dimension reduction would not be included. Automatic selection would implement the Bayes SGA. This algorithm uses 2 layers of classification. The subsets were determined using the highest variance for those attributes that had a UAV present. The K1 layer would do a local search, and those results would be passed on to the second layer, which is referred to as K2, and that would perform the global search and get the results. The user select would allow the user or analyst to choose 6 channels based on the cosine similarity matrix or the information from the box plots to determine the best candidates. The Wi-Fi data in the file was all continuous data. We assumed it was normally distributed, and we used the normal probability distribution density function here to calculate the probability for attributes, whether or not they contain a UAV or not. On this slide, I show the naive Bayes classifier we are using. In this case, we're testing 2 probabilities where an instance has a UAV present or an instance where UAV is not present. So here you can see we have the product with all the attributes AI, which are the columns in the Wi-Fi data, and we're iterating over each one of those columns depending on what D is. We have a certain, with the 3 modes, we have different sets of columns that we'll use, and so we'll calculate these 2 probabilities and be able to classify if that instance has a UAV or not. On this slide, this is the test that we use to once we calculate the probability for UAV being present versus UAV not present, if if the left is greater than the right, in this case, we classify that as UAV present. On this slide, I'm showing where the tool is training and then testing one of the models that was developed from this input file. You can see the error rate is at 0.00258, and FDR and FPR are 0. To the right, you see a confusion matrix that was visualized from the tool. The true positive, true negative is 1. So it's algorithm at this point is performing well. Here's an additional test of a model that was developed and it's being trained and tested. You can see the confusion matrix, and again, it's performing really well. The false positives and false negatives are 0, so it's very good results. On this slide, I'm showing the tool, how a user would detect UAVs. Once a user has a model loaded and they specified a data file, generally produced from Wireshark, they would be able to select the Run Model button. That's step number 1. And that would initiate the tool to start processing the data and run the algorithm that has been selected. The second step here is when the tool actually determines an instance has a UAV, and it will report by labeling the UAV detected label red, and it'll present a dialog box, alerting the user there's a UAV in the area. At this point, the user has to use a mouse to acknowledge it and dismiss it.
The algorithm we're using for clustering is called dbScan. It's the density-based spatial clustering of applications with noise. It's a density-based approach, so it's not based on centroid or distribution or grid algorithms. And it takes 2 parameters. Epsilon is the maximum distance that a point needs to be considered a neighbor of another point. Min points is how many points in that neighborhood that a point needs to be considered a core point. The advantages of dbScan is that the number of clusters is not required because it will just generate as many clusters as it finds. And it can also find noise, unlike other algorithms. The main disadvantage of dbScan is that it's hard to find the optimal epsilon in high dimensions because epsilon is based on the distance between points, which can be affected in high dimensions like what we're working with. The overview of the dbScan is that it starts by computing the neighbor of each point and identifying which ones are core points. It then joins the neighboring core points into clusters, and then for every point that's remaining, it will either add it to a core point or it'll classify it as noise. When we implemented the clustering algorithm, we evaluate the clustering performance by comparing it to the device label based on the file names. So for the bidirectional test, we had 4 devices, 1,200 instances, and it generated 3 clusters. The cluster to label correlation was 75% because it actually failed to generate the cluster for non-UAV, so only 3 out of the 4. The accuracy of the points that were clustered was about 96%. For the unidirectional set, we put a data file of 3 devices of 1,000 traces, and it generated 3 clusters. The cluster to label correlation was 100%, and the accuracy of clustered points was 100%. This shows a graph of how the unidirectional set came out. On the left, you see bar graph showing there's 3 different clusters, and they each have varying between sum of squares and sum of squared error. On the right, we have a cluster map, and this shows the size of the circles represents the size of the cluster. The distance between the cluster and the centroid is the Euclidean distance to the center of the data set. Also, the color of the node represents whether the cluster was majority UAV or non-UAV traffic. So in this case, we have two clusters that were UAVs, which represent likely two different models of UAV, and the blue circle represents non-UAV traffic.
So for our base classification, we conclude that our UAV detection tool successfully detects UAVs within the error rate we discussed during our proposal. Oftentimes we're seeing 100% or 0% error. Using a probabilistic algorithm, applying Bayes' theorem produces accurate results is what we're able to determine. And I was also interested in additional research using the SGA Bayes based on some of the testing that we've done. We got some good results where it oftentimes did better than the naive Bayes.
In conclusion, the dbScan algorithm groups packet captures into clusters that match the labels when the hyperparameters are properly tuned. However, it's not perfect because many points are classified as noise due to the high dimensionality of our data. And with the cluster results, we can create a model of what a UFE traffic pattern would look like.
We have a couple of recommendations for future enhancements. We weren't able to get to these due to the scope of the work and the schedule for the class. There's not only would you like to, in our case, identify as a UAV in an area, but the next thing you want to figure out is where it's at. And if we have, based on some of the research we have, if we have the multiple input files, we can add Doppler processing and we'll be able to perform location. It's not a trivial change. It's a fairly significant piece of work, but that's something that would be something worth pursuing. A second option would be more in the line as far as productizing the tool. We'd like to be able to add a feature to import and export models that were trained. That way we could distribute these to customers or users, and that would be a online repository perhaps, and or other ways to maybe to productize it. So it's a fairly trivial enhancement. It's something I didn't have the time to implement here, but as far as adding model identification, that would be the first step. This is a demonstration of the UAV detection tool using Bayes classification. I can select Bayes using the Classify Radio button and select the input file and the data file that I want to use for testing. Data ingest will read in the input data file here that was specified, and it'll display a cosine similarity matrix. The Bayes algorithms prefer to use attributes that are independent for best results, so I'd want to avoid using any attributes as on the diagonal that are 1.0. This is the angle between the same attribute. Using data prep, that'll display the box plots for the columns already selected here. I can use this to present new box plots by inspecting the cosine similarity matrix and identifying which columns I want to look at next. Using data train, here's the accuracy that's calculated. This is using the first input file to develop a test set and training set. It built a model, and then on the test set, it actually calculated what that looks like. We can visualize the confusion matrix. You can see here we have false positive of 0 and a false negative of 1. And here's the predictions for UAV present and not present. Again, run the model. This will be using the default mode. This will be using more of the brute force selection of attributes. Using the auto select, we'll use the SGA Bayes algorithm discussed during the presentation. You can see the numbers that were generated here. This is the number of classifications for UAV present using SGA Bayes. And then I can also select the user select, and this is where I would use the iterative process of choosing columns based on information I have here and in the box plots. And I can choose different attributes here. And I can run the model, and this provides me the results here.
To do clustering within our interface, we're going to start by going to the top left corner and selecting the file to cluster. This is going to take a CSV file based on the approved data format. And in this case, I'm going to use the 3 devices unidirectional dataset. And this one consists of 3 different devices, including 2 different UAVs that I've combined into one file so we can see whether or not the clustering algorithm breaks it up into 3 clusters. I'm going to select unidirectional flow because this data file has 19 attributes, which corresponds to this button. And then I'm going to set my hyperparameters. For this particular instance, I'm going to select 180 as the epsilon, and that's the distance that a core point needs to be within other points in order to classify it as a core point. The minimum points I'm going to leave at 100, and this is how many points a core point needs to have in its neighborhood in order to stay as a core point. Next, I'm going to ignore the classifier parameters and the select file to classify because those are for a different task. I'm going to do data ingest, which will show me that I have 1,000 rows and 19 columns, which corresponds to our data file. I'm going to notice there are cosine similarity matrix here so we can see how similar each of the attributes are with each other. I'm going to do data prep, and what this does is it will check to see if there's any missing values or extraneous values and discard them or replace them with the mean of the column. When I select data train, it's going to verify my hyperparameters and then tell me to run my model when ready. When I run the model, what it's going to do is go through each point and get the distance of that point to every other point. So for 1,000 rows, it could take about 20 to 30 seconds, and this is because it runs at a worst case of O of n squared time. When it's done, it'll give me this pop-up saying that it's ready for visualization. What that means is we can click on the Visualize button, and it's going to pop up 3 graphs here. The first graph shows the result of our clusters generated. We've got 3 clusters that were created, and this shows the between sum of squares and the sum of squared error of each of the clusters. So we see cluster 1 has the most error. This cluster map shows us the size of the cluster, the majority classification of the cluster, and then the distance of that cluster to the center of the data file. So we can see how far or close that cluster is to the majority of the data. The last file that's generated is the table, which shows us for each cluster what exactly the SSE was, the cluster size, count of UAV points, percent of UAV points, and then the distance to the dataset center. Lastly, when we go back to the main interface, we'll see that it tells us how many clusters were generated, the total points, and the points clustered. Any point that wasn't clustered is classified as a noise point. So in this case, it was a little over half of them that were classified as noise points. And that's a reality of the dbScan algorithm, which is one of its disadvantages, is that not all the points can be classified because of the way that the distance function works across so many dimensions. We can also see the total SSE and the total BSS. Lastly, if we want to see exactly what was in each cluster and we want to do analysis on it, we can go back to the console, and if we scroll up, we can see that it will give us the cluster number, size, and then it'll print out all of the row numbers that correspond to the data file that has these clusters. So you can see that it'll tell us which points were actually in the cluster. And since we created a data file which corresponds to different devices, we can go back and check that data file to see if points 0 through 250 correspond to a particular device. And in this case, they did because we labeled them as such. And cluster 2 was 250 to 500. So some of those points were put in this cluster. And the last cluster was 500 to 750. So some of those points were also put into this cluster. So we can see that the labels that were set up in the data file match with how the algorithm determined the clusters.